We are doing chapter 6, chapter 3 in lecture 6. And in this theorem, in this chapter, the great theorem is Euclid's proof that there are infinitely many prime numbers. So let's start by reviewing what is a prime number. So this is all part of what is called number theory, which is the study of the properties of the positive integers. Or more generally, just the integers. But in what we're talking about today, it's only positive integers. So we say that an integer d divides the integer n if n is d times q for some integer q. So this is the definition of divides or divisibility, which is fundamental. So for example, suppose we take the number 8. So 8 is 1 times 8. So 1 divides 8. 8 is also 2 times 4. So 2 divides 8. 8 is 4 times 2. So 4 divides 8. And 8 is 8 times 1. So 8 divides 8. And these are the only positive divisors of 8. So the positive divisors of 8 are 1, 2, 4, and 8. Of course, if a negative number divides 8, or if 2 divides 8, minus 2 divides 8, you could also say 8 is a minus 2 times minus 4. So minus 2 also divides 8. But that's kind of trivial, and we just usually write down the positive divisors and know that to every positive divisor, the corresponding negative number also divides 8. So as we take n equal 9. So 9 is 1 times 9. 1 divides 9. 9 is 3 times 3. 3 divides 9. 9 is 9 times 1. 9 divides 9. So in this case, the positive divisors of 9 are 1, 3, and 9. And it's fun. You can keep going. Let's take the next number, n equals 10. So the positive divisors of 10 are 1, 2, 5, and 10. All right. Each of those numbers divides 10 evenly with no remainder. What about n equal 11? The positive divisors of 11 are 1 and 11. There aren't any others. What about n equal 12? What are the positive divisors of 12? Can someone?
1, 2, 3, 4, 6, and 12.
Excellent. There are a lot of them. What about n equal 13?
1 and 13.
What about 14?
1, 2, 7, 14.
Okay, excellent. Now, we notice that for every integer n, we have n is 1 times n, and n is n times 1. So every integer n is divisible by 1 and by n, right? Every number has at least, every number bigger than 2, or at least as big as 2, always has at least 2 divisors. And we notice there's some numbers, like n equals 11 and n equals 13, where the only divisors of the number are itself and 1. And such a number is called a prime number. So a prime number, or a prime, is an integer n, at least 2, whose only divisors are 1 and n. For example, 11 and 13. Their only divisors are itself and 1. And if a number is not prime, it's called a composite. So a composite number is an integer n greater than or equal to 2 that is not prime. So for example, if you look at this 10, 12, and 14, so an integer is prime if it's at least 2, and its only positive divisors, I should say positive, this -1 divides the number also, whose only positive divisors are 1 and n. A composite number is an integer at least 2 that is not prime. What about n equal 1? So the integer n equal to 1 is just n equal to 1. So this is neither prime nor composite. So what is it? It's 1. Okay. So, and you might say prime numbers are like atoms in the periodic table. In chemistry, every molecule consists of atoms, right? So water is H2O. One molecule of water has 2 hydrogen atoms and 1 oxygen atom. So in arithmetic, in mathematics, every positive integer, so think of a positive integer as sort of like a molecule, is a product of prime numbers in a unique way up to order. So let's just write down the first positive integers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and write them as a product of primes. Well, 1 is just 1. It's a product of no prime. Or if you want not to have to worry about 1, you can say every positive integer greater than or equal to 2 is a product of prime numbers. 2 is a prime. It has only divisors are itself and are 2 and 1, and 2 is a product of 1 prime. 3 is a product of, is prime. It's just product of 1 prime. 4 is 2 times 2. 5 is 5. 6 is 2 times 3. Now you might say 6 is also 3 times 2. So this is another way to write 6 as a product of primes. Here 2 comes first and then 3. Here 3 comes first and then 2. But it's the same primes, they're just in a different order. So that's what I mean when I write every number is a product of primes in a unique way up to order. You can rearrange the primes, but the same primes occurring the same number of times. 7 is a prime. 8 is 2 times 2. You can't write 2 times 4 because 4 is not a prime. 2 is 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. 11 is a prime. 12 is 4 times 3. 4 is 2 times 2. It's 2 times 2 times 3. 13 is a prime. 14 is 2 times 7. 15 is 3 times 5. 16 has 4 primes. It's the prime 2 occurring 4 times. 17 is a prime. 18 is 2 times 9, and 9 is 3 times 3. 19 is a prime. 20 is 2 times 10, but 10 is 2 times 5. Right? So just so you get a little bit of the fun, spend a minute and write each of the numbers from 21 to 30 as a product of primes. You know, just take a piece of paper and jot down the answers. What is the prime factorization of 21? 3 times 7. 22. 2 times 11. 23 is prime. It's just 23. On the other hand, 24 has a lot of prime divisors.
It's 2 times 2 times 2 times 3.
Excellent. Yes. 25.
For 25, I have 5 times 5.
Good. Anyone else want to chime in? 26.
2 times 13. Mhm.
All right. 27.
Is it 3 times 9?
Right, but 9 factors.
Right. So 3 times 3 times 3.
Yeah. So this is now you have to write it just as prime product of prime numbers. So yes, that's it. 28.
2 times 2 times 7.
Excellent. 29.
I have 1 times 29.
Well, you don't need the 1, just write 29.
Well, just 29. Yeah.
And 30.
2 times 3 times 5.
Excellent. So if you look at this list, some of these numbers are prime. 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Actually, quite a few. But if you look at, so this is a range of 30. If you look at the numbers from 1,000,001 to 1,030,030. That's also 30 consecutive numbers. How many numbers there are prime? Actually, let me take advantage of the fact that I have Maple on my computer, and Maple can factor numbers very quickly. So let me see if I can share the screen with a Maple worksheet. Again, if you don't have Maple or no Maple, it's fine. It's just nice to know that there are computer algebra programs that can do a lot of things for you. So I could say for n from 1,000,001 to 1,030,000 do. And this I just want to write down the primes. So if n is prime, then print n. Let's see if this works. Oops. N is spelled with a D. Ah, so there's only one prime in that range of 30. Let's just double check what we did a moment ago. A moment ago, we looked at the primes from 1 to 30. Yeah, compare that to the list we got. Yeah, it's exactly the same. So either we're no smarter than Maple, or Maple is no smarter than we. On the other hand, Maple can do calculations a lot faster than we can. Like, suppose we wanted to find all the primes. I could say from 1 to 1,000,000, but it would take, oh, I'm curious. Let's see. Write down all the primes from 1 to 1,000,000. There are a lot of them. I'm actually going to stop this because it'll take too long, but this just went up to, I stopped at about 11,000. So yeah, these are all primes. Suppose instead of printing them all out, I just want to count how many there are. So let me change this program. Let me start with the counting. Let's say L. It's just going to count how many primes there are. So now I want to say for n from 1 to 1,000,000, if you have a number that's prime, add 1 to this counting number. Replace L by L plus 1. And let's try this. Printing is hard in Maple. Oops. Oh. It's a long calculation, I guess. Oh, all right, that's the answer. From 1 to 1,000,000, there are 78,498 primes. But it'd be impossible to predict this without doing the calculation. Suppose you want to divide this interval up into intervals of 100,000. So let me change this. Let me change my program. So for L from 1 to 10, do. So, and what I want to do is for let's say M from N times 10,000 plus 1 to N times 10,000 do. So I want to make this N minus 1. So this is like when N is 1, this is going to go from 1 to 10,000. When N is 2, this is going to go from 10,001 to 10 and so on. If, actually, I don't need that. Let me try calling this. I'm just trying to write a program which will count the primes in let's see if this works. Oops. What's the problem here? Oh, that should be a capital L. Let me try that again. Let's see if just this works. N goes from 1 to 10. For each N, let L of N equal to 0. And then as you run through this interval of 10,000 numbers, if is prime M, then add 1. Let's see if that goes. Okay. That's all right. Let's try this. Okay. Here we go. So in the first 10,000 numbers, there are 1229 primes. In the next, there are 1033, 980. So as you go through successive pairs of 10,000 numbers, these numbers aren't strictly decreasing, but they're sort of getting smaller. Yeah. Let's go through a bigger range. I'm just curious what these numbers look like. Yeah, wow. So I just went up to 20 million. So in intervals of 10,000. And yeah, not changing, it's decreasing a little bit. Kind of interesting. What's really interesting is what you can do with a tiny bit of knowledge of Maple. But those are prime numbers. Now, you might ask, I made one statement about prime numbers already. And you might ask, how do I know that it's true? And the statement was that every number is a product of prime numbers, and not only a product of prime numbers, but a product of prime numbers in a unique way. So let me just sort of sketch why this statement is true. Okay. That every positive integer is a product of prime numbers in a unique way up to order. And this is sometimes called the fundamental theorem of arithmetic. That every number not only is a product of prime numbers, but in a unique way. And the key to that is something which is called Euclid's lemma, among other things, because it's in Euclid. And it says the following: if P is a prime number, if P is prime, and P divides the product of two numbers A and B, then it divides at least one of them. P divides A, or P divides B. So for example, $98, let's see, if I divide that by 7, I get 7 times 14.
Professor, can you pull your paper down a little?
Oh, sure.
Thank you. Thanks.
So this is Euclid's lemma. It says, if P is a prime and P divides a product of two numbers, then it divides one of them. So maybe a better way to say this is the following. 7 divides 189, right? Why is that? 189 is 7 times
27?
Yeah, 7 times 27. So 189, you could also write this as, for example, 21 times 9. Right? 7 divides the product of these two numbers, and 7 is a prime, so it has to divide one of them. And in fact, 7 does divide 21. So here I have a prime that divides the product of these two numbers, and in fact, it divides one of them. Suppose a number is not prime. Let's see, 6 divides 10 times 15, which is 150. Let's see, 6 into 150 is 25, right? So 6 divides 10 times 15, but 6 does not divide 10, and 6 does not divide 15. So here I have 6 dividing a product of two numbers, but it doesn't divide either one of them. Here, 7 divides a product of two numbers, and because 7 is prime, it has to divide one of them. So this is a fundamental property of prime numbers. If a prime divides the product of two numbers, it has to divide one of them. And suppose you know that. So let's start with n. So let n be an integer greater than or equal to 2. I want to show n is a product of prime numbers. Just that. Every integer at least 2 is a product of prime numbers in at least one way. Okay. And we start with the following sort of fact, if you like. If a strictly decreasing sequence of positive integers must stop after finitely many steps. What I mean is you have a number n1. These are all positive integers. So these are integers and they're all greater than or equal to 1. They're all positive. Bigger than n2, bigger than n3. This is strictly decreasing. Each term of the sequence is strictly smaller than the one before it. It can't go on forever. If these are integers, it has to stop after a finite number of steps. All right. So let me just to observe, this is not true for numbers that are not integers. For example, it's not true for fractions. You could have the number 1 bigger than, these are going to be positive fractions, bigger than a half, bigger than a third, bigger than a fourth. This goes on forever. This is an infinite, strictly decreasing sequence of positive rational numbers, positive fractions. So you can have an infinite, strictly decreasing sequence of numbers that are positive, greater than 0, positive, that aren't integers. But if they're integers, any strictly decreasing sequence has to stop at some point, right? It can't go on forever. So this is one of these things that is kind of obvious if you think about it, but you have to think about it and think of writing it down and realize how important it is. So let's just show how we use that here. Suppose n is a positive integer. I want to show n is a product of primes. So if n is prime, we're done. N equals p. It's a product of one prime. If n is composite, that means it factors. N can be written as n1 times n2, where n1 is strictly less than n, and n2 is strictly less than n. Now, if these are primes, I'll call it n1 and n1 prime. If these are primes, we're done. So if n1 and n1 prime are primes, we're done. If not, one of them is composite. Say n1 is composite. So I can write n1 is n2 times some other number as factors, where n2 is less than n1, which, by the way, was less than n. Now, If both of these numbers are prime, we're done. But if one of these is composite, if n2 is composite, then n2 factors into n3 times n3 prime, where n3 is less than n2 is bigger than 1. But n2 was less than n1 and n1 was less than n. So this is really an argument you have to think about for a while in some quiet place with some paper and pencil maybe. Take an integer n. If it's prime, you're done. Otherwise, it's composite, so it factors. So it's a product of two smaller numbers. If n is not, so think of it, let me state it like this. Suppose you have an integer n, which is not a product of prime numbers, right? So I want to show that leads to a contradiction. Suppose n, an integer greater than 1, is not a product of prime numbers. So you can write n as n1 times n1 prime. It factors, and at least one of these numbers is composite. Right? Say n1. But if n1 is composite, you can factor it. And if this is a product of prime numbers, you're done. Otherwise, n2 is a composite, so n2 factors. And you can continue this process of factoring, and you generate some sequence of positive integers, which is strictly decreasing. And that's impossible, right? This cannot be an infinite sequence. Of strictly decreasing positive integers. So that's one way to give this argument. There's another way, if you know what is called mathematical induction. So there's an equivalent statement which says, if you have any set of positive integers, it contains the smallest element. Right? Take any set, non-empty set of positive integers, it contains the smallest element. Because if it didn't, you could choose any element in it, and then there would be in the set, then there would be a smaller element in the set, and then there would be a smaller element than that in the set, and you would generate this infinite decreasing sequence of positive integers. So every non-empty set of positive integers contains the smallest element. So this is a simple principle. Called the minimum principle. Every non-empty set of positive integers contains a smallest or a minimum element. So suppose we let X be the set of positive integers, or integers greater than the set of positive integers greater than or equal to 2 that are not products of prime numbers. So I claim that every number 2 or greater is a product of prime numbers, and I'll prove that by contradiction. Suppose if you look at all the numbers that are not product of primes, that set is not empty. Okay. So if X is not empty, then X contains a smallest element, a smallest integer, n. So n is the smallest number that is not a product of primes. And certainly n is not prime. So n is composite. So n is a product of two numbers, n1 and n2, where n1 is less than n, and n2 is less than n. Right? So n is the smallest number that's not a product of primes. So it itself cannot be a prime. So it's composite. So it factors into a product of two numbers, each strictly smaller than n. But then n1 is a product of primes because it's smaller than n. And n was the smallest integer, not a product of primes. And n2 is also a product of primes, because n2 is less than n. And then we have a contradiction because n is n1 times n2, and 1 is a product of these k primes, and n2 is a product of these L primes. This is a product of primes, which is a contradiction, right? That's a proof by contradiction. So we're done. So every number is a product of primes. And to prove uniqueness takes a little bit more work. And it depends on Euclid's lemma. But since this is not a class in number theory, and since it's not a proof that the author gives,
Professor, can you go to the minimum principle?
yeah, it says if you have a set of positive integers, it contains the smallest element. That's all, a minimum element. So for positive integers, I mean, if you take the set of all integers, there's no minimum element because you have all the negative numbers going to minus infinity. But if you're only looking at positive integers, every non-empty set of positive integers contains the smallest element, right? I mean, if the set contains 15, maybe 15 is the smallest. If not, there's something smaller than 15. Maybe it's 8. If 8's not the smallest, there's something smaller, like maybe 6. But you're only looking at positive integers, so you can't continue this process forever. And after a finite number of steps, you get to the smallest number in the set. That's what we're saying.
Okay, thank you.
But again, this is one of those things which almost no one would ever think of. But once someone thinks of it and tells you, you say, yeah, it's obvious, it's clear. Like, you can't have positive integers getting smaller and smaller and smaller because they all always have to stay above 0. And they're integers. You can't go like a fractional step. They always go down by at least 1. So
And
forever.
and plus, the completeness axiom isn't in the integer set, so there has to be like
Right, it's
the
not like the real
smallest.
numbers. The
Yeah.
real numbers can go down forever, right? I mean, if you look at the interval from 0 to 1, you know, you can get smaller and smaller numbers. You can get an infinite, strictly decreasing sequence of real numbers or of fractions, but not of integers, right? Because you can't go down by a little step. An integer, a smaller integer, one integer smaller than a number is smaller by at least a whole unit 1. And so you go smaller and smaller, but eventually you have to stop.
Yeah, exactly my thoughts. Thank you.
Mm-hmm. Yeah. I mean, it's like a surprisingly important fact. But okay. Now, every number is a product of primes, and it could be like there are only finitely many primes. It's sort of like if you look at Mendeleev's periodic table in chemistry, it lists all the atoms, and there's a relatively small number of them. Like they're not 1,000 different atoms. They're not 500 different atoms. There's, 100 or less maybe. That's it. And every molecule in the universe is made up, well, we don't know about the universe, but every molecule on Earth certainly is made up of atoms. So, and it could be there's like some enormous number of prime numbers, and every integer is a product of primes in that finite set. And the great theorem in this chapter, due to Euclid, is that the number of primes is actually infinite. So there's like a strange way, I mean, Euclid's language as it's translated is a little bit unusual for us. This is in book Roman numeral 9, proposition 20. And this is the way this is translated from Greek into English on page 73 of our book is the following. Prime numbers are more than any assigned multitude. And the way we would state this is there are infinitely many prime numbers. So when you start to write down the primes, 2, 3, 5, 7, 11, 13, 17, 19, and so on, this goes on forever. It never stops, right? So however big a number you choose, there's always a prime bigger than that number. And Euclid's proof, which is really one of the great proofs in mathematics, and you could teach this to fairly small children even, is a proof by contradiction. So I'll use the notation that's used in the text. Suppose A, B, C, and so forth up to D are prime numbers. So this is a finite set of prime numbers. Must show there exists a prime not equal to A, B, C, and so forth, not equal to any of these numbers. So I have a finite list of primes, and I have to show that's not all there are. There must be another prime. So Newton's brilliant idea, sorry, not Newton, Euclid's brilliant idea is to let n, if you have a finite set of numbers, you can multiply them together. So multiply together A times B times C, all these numbers up to D. That's this product of prime numbers, and add 1 to it. Okay? So this is a number bigger than 1. So this is either prime or composite. If n is prime, then n is certainly bigger than A, n is bigger than, because you're taking all these numbers, A, B up to C, A, B, C up to D, n is bigger than C N is big, it's bigger than each of these numbers because it's this product plus 1. So if n is prime, then n is bigger than A, B, C, or D, and we're done. We found a prime not in this finite set. Right? So this happens to be prime. We're done. That's case 1. Case 2, n is composite. So in that case, there is a number G bigger than 1 that divides n. So let's say n is equal to G times some number Q. Now, if this number G were equal to A, then what could we say? We would have n, which is GQ, but if G is equal to A, that's AQ. And n itself was this product A, B, C up to D plus 1. If I just rearrange this, means 1 is AQ minus this product. And you notice in this, I have the number A occurring, so I could factor it out. So this is A times Q minus the product of B, C, and so forth up to D. So 1 is this product, but the only way 1 factors is 1 times 1. So A equals 1, which is false because A is prime. Prime number is greater than or equal to 2. So in the second case, I assume this number n is the product of these primes A, B, C up to D plus 1. If n is composite, it's divisible by some number G between 1 and n. Right? That's what it means to be composite. Now, if G were one of these primes, say G were equal to A, I would rearrange the equation and get that A equals 1, which is false. Because A is a prime, and a prime number is at least 2. So this divisor G, in fact, not only is there a number G that divides n, there's a prime number that divides n, because every number is a product of prime. So there's a prime number G that divides n, and G can't be equal to A. And by the same argument, it can't be equal to B or C or anything up to D. So we have a new prime. G greater than 1, this is a new prime, not equal to any of the numbers A, B, C, or so forth up to D. What I just proved is, if a finite set of numbers, is there a question? Given any finite set of prime numbers, there's an additional prime not in that set. So the number of prime numbers has to be infinite. And that is the great theorem. And it is 100% certain that on the midterm or the final or both, you'll be asked to prove this theorem, because you cannot take a course in the history of mathematics and not walk away with a knowledge of Euclid's proof that there are infinitely many primes. It really is a great theorem, and it's worth spending a lot of time studying it. Prime numbers themselves are very mysterious. So for example, if you look at our list of primes, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53. It goes on forever. You see, sometimes, first of all, the only even prime is 2, right? 2 is a prime, but any even number is divisible by 2. So any even number other than bigger than 2 must be composite. So other than 2, all these numbers are primes. So primes are odd. So the closest 2 primes can be to each other is to be consecutive odd numbers, like 3 and 5, or 5 and 7, 11, 13, 17, 19. 29, 31, 41, 43. So primes P and Q that differ by 2, or in other words, primes that are consecutive odd integers, are called twin primes. So they're primes that are as close together as they can possibly be. And there are a lot of twin primes. We know there are infinitely many primes, but there is a question. Are there infinitely many twin primes? That is, primes P such that P plus 2 is also prime. These are twin primes. And this is a question which is still unanswered. It's an open question. This has been an unsolved problem in mathematics for 2,000 years. Are there infinitely many twin primes? I mean, there are a lot of them, like 101 and 103 are twin primes. Yeah. I mean, you can ask Maple to look for twin primes. Let me see if I can, on the spur of the moment, write a little Maple program to look for twin primes. Let's see. For n from, let's just start from 3 going up by 2, because I'm looking at by 2 to 1,000. Let's see. So in this loop, oops, if n is prime and n plus 2 is prime, then print the pair n plus 2. Let's see if this works. Oops. One time loop. For n from 3 to 1,000. Oh, I forgot the word. Do. You have to tell it what to do. If n plus, oh, sorry, that's stupid. Is prime doesn't make sense. If n is prime and n plus 2 is prime, then print. Wow, okay, here we go. Look at this. This is fascinating. I mean, this is like a trivial program. It's like basically a one-line program in Maple. These are all the twin primes up to 1,000. Let's keep looking. This is fun. Let's go up to 3,000. Oh my God. By the way, it is amazing how fast Maple is. And this is on a very old computer that I have now. These are all the twin primes up to 3,000. Okay. Like 1697 and 1699 are consecutive odd numbers that are primes. Look at that. That's pretty good. So there seem to be a lot, but who knows? This is an open question. Here's another open question. If you take odd primes, the sum of two odd numbers is even. Let's see, so let's say you take 6. That's an even number, but I can write it as 3 plus 3. 8 is 3 plus 5. I'm writing these even numbers as sums of two odd numbers, but in fact, I'm writing each even number as a sum of two odd primes. Like 10 is 3 plus 7, or 5 plus 5. I can write 10 as a sum of two odd primes in different ways. 12 is 5 plus 7. 14 is 7 plus 7. I mean, there are other ways I can do it. I can also write 14 as 3 plus 11, but I just want to find one way to write an even number as a sum of two odd primes. 16. 18 is 7 plus 11. 20 is 3 plus 17. 22 is 5 plus 17. 24 is 7 plus 17. 26 is 13 plus 13. 28 is 5 plus 23. 30 is 7 plus 23. And if you keep looking, it seems that whenever you look, you can write the number, an even number, as a sum of two odd primes. Huh. Let me try again with Maple and see if I can write a program to write an odd number, an even number as a sum of two primes. So let's say for n from 3 to 100 do. Or maybe I'll do it like this. For n, I'll start at 6, going up by 2 to 100 do. And what do I want to do? For k from 3 by 2 to n minus 1 do. And what I want to do is if k is prime, and if n minus k is prime, then print n, k, n minus k. And, so let's see. I'm going to go through the even numbers from 6 to 100. And I want to write each number, if possible, as a sum of two odd primes. So if k and n minus k are prime, then there are two primes that add up to k. So let's see if this works. Oops. I didn't do it. Huh. For n from 6 going up by 2 to 100. For k going up through the odd numbers from 3 to n minus 1. If k and n minus k are prime, then print this. All right, I have to put a space in there. Okay, here we go. It's taking a while, but here's the answer. Look at this. Okay. 6 is 3. This is not only going to write each number is a sum of two odd primes, but every possible way. And in fact, I have it 3, 5 or 5, 3. I should have made this not 2. N minus 1 divided by 2. That way I don't get multiplicity. So okay, here we go. It's quicker. So if you look at this table, every even number has at least one representation as a sum of two odd primes. 8, 10, 12. I'm not skipping any even number. Okay. 60 is 7 plus 53, 13 plus 47. A lot of different, oh my God, look at this. 60 is a sum of two odd primes in 1, 2, 3, 4, 5, 6 different ways. Wow, that's interesting. All right. So however far you look, and people have looked very far, they've always discovered some way, at least one way, to write an even number as a sum of two odd primes. But this is also another open problem in mathematics. It's called the Goldbach conjecture, after a mathematician named Goldbach who made this conjecture. Every even integer, n, greater than or equal to 6, is the sum of two primes in at least one way, right? And no one for hundreds of years has been able to solve this problem. Any questions so far?
No,
Oh,
Professor.
yeah, go ahead.
Oh, I was saying no questions on my end.
Oh, okay. All right. So again, this is all really important mathematics in number theory, and it starts with Euclid. So you have to remember, Euclid is not just about geometry. He also includes other parts of mathematics, including, as we see here, number theory. In geometry, we've looked at so far triangles, squares, such things, but Euclid also considers three-dimensional geometry, solid geometry. So this is in book 13. Actually, books 12 and 13. We consider solid geometry. These are shapes in three-dimensional space. You, for example, you can have a box, which is sometimes called a parallelepiped, or a sphere, or a cone. Or a pyramid. So these are solid figures in three-dimensional space. In R3 is what you call it in calculus. And the Greeks were fascinated by questions of symmetry. So, for example, in the plane, they love things like the equilateral triangle. Or the square. Or a regular pentagon. So these were figures where all the sides have the same length and all the angles are the same. So these are so-called regular polygons. They have equal sides and equal angles, right? So in the equilateral triangle, every angle is pi over 3 radians or 60 degrees. In the square, every angle is a right angle, pi over 2 radians or 90 degrees. In the regular pentagon, every angle is 3 pi over 5 or 108 degrees. And so on. So what is the analog in space? So in space are what are called regular polyhedra. The singular is polyhedron in space. So these are figures where every face is a regular polygon and all solid angles are equal. So what are some examples? Well, the simplest is a cube. In a cube, every face is a square. What does it mean to have a solid angle at a vertex? At a vertex, you have different faces that are adjacent to that vertex. And each face is a polygon in 2 dimensions, so it has an angle. Here's an angle, here's an angle, here's an angle. And the sum of those 3 angles is the solid angle. So in terms of degrees, each face has a right angle at the vertex. So the sum of these faces is 3 right angles, which is 3 pi over 2 or 270 degrees. And that's the same at every vertex. Another polyhedron, regular polyhedron, has every face an equilateral triangle. So this is called, there are four faces, four in Greek is tetra. This is the tetrahedron. Now, in the plane, you can have a regular polygon of any number of sides. Here, 3 sides, 4 sides, 5 sides. You have a regular hexagon. And so for any number of sides, there is a regular polygon with n sides for all n greater than or equal to 3. You may not be able to construct it with ruler and compass, straight edge and compass, but you can see how it can be constructed. What about the regular polyhedra? Can you have infinitely many regular polyhedra? And the answer is no, and this is a beautiful theorem in Euclid, which says there exist exactly 5 regular polyhedra. And the cube and the tetrahedron are easy to draw. The other 3 are more difficult. So you have to look at page 79 in your text. These are the 5 regular polyhedra. Here we have the tetrahedron. So we have 4 sides, and each face is a triangle. We have the cube, which has how many faces? 4 as you go around, plus top and bottom. So there's 6 sides or faces, and each face is a square. Actually, if you look at the tetrahedron, you have 4 faces. How many edges? So you have 1, 2, 3, 4, 5, 6. 6 edges. And how many corners or vertices? 1, 2, 3, 4. 4 vertices. So you have 4 faces, 6 edges, and 4 vertices. What about for the cube? You have 6 faces. How many edges? You have 4 in the front, 4 in the back, and 4 when you go around. So there are 12 edges. And how many vertices? 4 in front, 4 in back, 8 vertices. Now, the next are much harder to draw. There is something called the octahedron. Hedra means side, octa means 8. So this is going to be a figure with 8 sides. Imagine a square. The square is not there, but, and you take a vertex above the square and you put an equilateral triangle going from the vertex on the top to the 4 sides of the square, and the same from the bottom. So you have 4 triangular faces on top and 4 triangular faces on the bottom. So this octahedron has 8 faces. Each face is a regular triangle. Let's see, can we count the number of edges? 4 on top, 4 on bottom, and 4 around the middle. So 12 edges. And how many vertices? 4 around the middle and 1 on top and bottom, so 6 vertices. Now, the next two are more complicated yet. So there is something called the dodecahedron. So hedron means side, deca is 10, do is 2, 2 plus 10 is 12. So this is going to be a regular polygon with 12 faces, and each face is a triangle. And, sorry, each face is not a triangle, it's a pentagon. You sometimes see this as like a item on people's desks. They have this thing has 12 faces and they put a calendar on each face though. So it's like each face is a pentagon. And I truly cannot draw it. You have to look at the book to see this dodecahedron. It has 12 pentagonal faces. And at each face, at each vertex, you have 3 pentagons. Now, how many different vertices are there? And how many different edges are there? If you know there are 12 faces, each face has 5 vertices. But in the 3 face, so altogether, if you looked at each face separately and counted the number of vertices, there would be 60 vertices. But you have 3 vertices coming together at each corner. So 60 divided by 3, you have 20 vertices altogether in this thing. Similarly, if you have 12 faces and each is a pentagon, each face has 5 edges. So you have 5 times 12, you have 60 edges, but they come together in pairs. So when you look at the dodecahedron, you have 30 edges. So this is something you have to think about a bit. And then the last figure, which is completely hopeless for me to draw. There, that's the picture. This is called the icosahedron. So this has 20 faces. Each is a regular triangle. And at each vertex, you have 5 triangles meeting at each vertex. Now, if you have 20 faces and each face is a triangle, each face has 3 edges. So you have altogether 60 edges on the triangle separately, but on the tetrahedron, they come together in pairs. So you end up with 30 edges. And each triangle has 3 vertices. So you have 60 vertices, but you have 5 triangular vertices meeting at each vertex of the icosahedron. And that gives you 60 divided by 5, 12 vertices. So you have to look at the picture in the book to see these things. And these are all there are. There aren't any more. So maybe tomorrow I'll start by giving Euclid's proof that these are all they are, and then we'll move on to the next chapter. But there is a remarkable coincidence, if you like, between these 5 figures. So in each figure, you have the number of faces. I'm sorry. Yeah, well, the number of faces. And you have the number of edges and the number of vertices. And there's the following sort of numerical magic. The number of faces minus the number of edges plus the number of vertices in all of these figures equals 2. That is a very important geometrical observation. Faces minus edges plus vertices equal 2. And if you study more geometry, then you learn why this is the case. Okay. Any questions about what we were talking about today? We were talking about a lot of mathematics, a lot to learn, so. I'll post a homework today, which will be due next week, a homework on chapter 3. And then starting tomorrow, we do chapter 4. Following the rule that every week we do a chapter. So this is the 6th lecture, 2 lectures a week. So the 4th week starts tomorrow, Thursday, and we will prove a theorem of Archimedes. Yep. All right. If there are no